Hello, welcome to EPG Pathshala. This module is on classical laws of bibliometrics. After going through this module, you will know the classical laws of bibliometrics, learn the formulae pertaining to the laws, be able to apply the laws in a library environment, and educate yourself as to how these laws are verified. Classical laws in bibliometrics include Bradford's law of scatter, the three laws of Ziff, and Lotka's law. These are purely scientific laws. They have well established formulae, and the concepts embedded in them are less likely to change with time. Moreover, their validity can be verified scientifically. Bradford's law of scatter. The law was propounded by Samuel Clement Bradford, a British librarian, mathematician, and documentalist at the Science Museum in London, after a laborious study of scientific literature in the mid 1930s. After examining the distribution of scientific literature in periodicals and their coverage in abstracting and indexing periodicals, he realized that the distribution of literature follows a particular pattern. He opined that the nucleus of periodicals devoted to the given subject must contain individually more articles on that subject than periodicals dealing with related subjects. In consequence, it is possible to arrange periodicals in zones of decreasing productivity in regard to papers on a given subject, and the number of periodicals in each zone will increase as their productivity decreases. Finally, the law took the shape as given in the definition below. Definition of Bradford's law of scatter. If scientific journals are arranged in order of decreasing productivity of articles on a given subject, they may be divided into a nucleus of periodicals more particularly devoted to the subject, and several groups or zones containing the same number of articles as the nucleus. When the number of periodicals in the nucleus and succeeding zones will be as 1 is to n to the power 2. Explanation of Bradford's law of scatter. The phrases scientific journals and decreasing productivity of the articles need explanation. The law is applicable generally to scientific journals. It may or may not be applicable to the journals of other fields, books, and other types of documents. The number of articles pertaining to a journal is called its productivity. In the table, the data is arranged according to the decreasing productivity of journals. For example, if the productivity of journal A is 74 and journal B is 85 and B second. Explanation. In a situation where the data ideally suits Bradford distribution, the set of journals, say numbering 310, would be divided as 10, 10 into 5 and 10 into 5 into 5. The first 10 journals will belong to the core zone, the next 50 to the allied zone, and the last 250 to the alien zone. The number of papers in each zone will be the same. In reality, we do not get such data that perfectly satisfies the law. In most cases, the data satisfies the law roughly. Verification. Data is to be tabulated in 4 columns as given below. Here, only the first few rows and the last row is shown. The full table may be seen from the text. The table given above needs some explanations. The periodical having the largest number of articles, that is 93 ranks first, followed by periodicals ranking second, third, and so on. In the ranking, at times, two or more periodicals occupy the same rank. For example, four periodicals ranked 13th with 6 articles each. In such a case, all are given the 16th rank, because if we give all the periodicals 10th rank, then it would seem as if there are 10 periodicals. In fact, there are 13 periodicals. By seeing the last rank in the table, we easily know the total number of periodicals contributing to the literature in the field. In actual studies, the name of the periodical is also given along with the rank number. When the number of periodicals is very high, to shorten the size of the table, the names of the periodicals are given, say up to 50th rank or even less. Distribution of articles according to zones. The articles n is equal to 1332 are to be divided into 3 equal parts. Each part should have 1332 is to 3 is equal to 444 articles. In most cases, they will not be exactly equal. It is to be seen that the number, that is the whole number, matches a particular rank. Suppose in a table, the 9th rank matches with 429 and 10th rank with 445. As 445 is close to 444, hence in the first zone, the 10th rank is selected. Similarly, articles of the second and third ranks are selected with their corresponding number of periodicals. From the data, we get the value of n as 49 by 10 is equal to 4.9. Multiplying 49 by 4.9, we get 240, which is close to 267. The ratio of the periodicals is 10 is to 49 is to 267, which is roughly 1 is to 5 is to 5 to the power 2. For drawing the bibliograph, take y-axis for the number of periodicals and x-axis the number of articles. The graph may be plotted in a semi-log paper. The computer literates may draw the graph using a computer. Bradford Bibliograph. In this graph, x-axis is partial sum of journals in log scale. Y-axis is the partial sum of articles contained in X topmost journals in a linear scale. Uses of Bradford's law. It depicts the spread of the journal literature on the subject. The subjects of the journals harboring the literature shows how enormous are the spread and the journal variety. It helps to identify the core periodicals in a subject. Also, it throws light on the allied and alien periodicals pertaining to the subject. It produces a ranked list placing the journals according to their productivity in descending order. It helps a great deal in the selection of periodicals. Due to budget crunch, when certain periodicals need to be deleted, usually the lower ranked periodicals are deleted. Ziff's laws. George Kingsley Ziff, an American linguist, propounded 3 laws of linguistics, of which the second law is usually taught in our LIS courses. Ziff's first law. If the number of different words occurring once in a given sample is taken as x, the number of different words twice, 3 times, 4 times, n times in the same sample is respectively 1 divided by 2 to the power 2, 1 divided by 3 to the power 2, 1 divided by 4 to the power 2, 1 divided by n to the power 2 of x, up to, though not including, the few most frequently used words. That is, we find an unmistakable progression according to the inverse square valid for well over 95% of all the different words used in the sample. For example, if in a sample 144 words are occurring only once, then the number of words occurring twice will be roughly 36 and occurring thrice will be roughly 16. Basing this phenomenon, Ziff developed the formula AB square is equal to K, where A is the number of words occurring B times and K is a constant. Ziff's second law. Definition: the conspicuousness or intensity of any element of language is inversely proportionate to its frequency. Here, conspicuousness or intensity means rank. Equation: using x for frequency and y for conspicuousness or rank, the law can be mathematically expressed as y infinity 1 by x. xy is equal to n, where n is a constant. The definition can be stated in simpler terms as the rank of any word of a language is inversely proportional to the frequency of its usage. The lower the rank, the higher will be the frequency. Verification. Manual verification is pretty difficult and time consuming. It can be best verified using a scanner, a computer, and a suitable programming language. When the words of a piece of writing has been arranged and their frequencies calculated, then prepare a table as given below. Check the values of the third column. If they are more or less the same, the law is verified. Ziff's third law. Definition: the length of a word is very closely related to the frequency of its uses. The greater the frequency, the shorter the words. If you count the length of words taking a dictionary, you will find that there are more words with 4 letters compared to words with 8 letters. Lotka's law. Alfred James Lotka, a US statistician, mathematician, physical chemist, and famous for his work in population dynamics and energetics, propounded the law that is named after him. Definition of Lotka's law. The number of authors, say Y, making X contributions in a field during a specific period of time is about 1 divided by x to the power n of those making one contribution each, where n nearly equals 2. Equation. The equation derived from the study is x to the power n y is equal to c, where x stands for the number of contributions, y stands for the number of authors, and c is constant. Verification. Take an author index of an abstracting or indexing periodical. You can take the whole A to Z index if the number of entries is manageable. Otherwise, you can take part of the index. Count the number of entries against each author and write down the number against his name. Let us call this the productivity of the author. If this data is entered into a computer, sorting of the data will be easy. It can also be done manually, recording the data on cards. Take about 30 cards, number each card serially from 1 to 30. In the card number 1, write down the number of authors who have contributed one paper each. Similarly, in card number 2, record the number of authors who have contributed 2 papers each. Continue the process till you reach the author who has made maximum number of contributions. Remember, the name of the author is not to be written on the cards. Arrange the cards according to serial number and prepare a 2-column table as given below. Prepare a 2-column table as given below, presenting the data in an ascending order. Taking the value of n as 2, check whether the data fit into Lotka's law. If it does not, you are to try with different values of n. It may be more than 2 or less than 2. By trial and error method, you may arrive at a value that will bring the figures quite close to the actual values.